Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
High-performance programming language. Before Brad joined Cray, he worked at, he was a student at University of Washington and did his PhD there. He worked on ZPL, which, if people know, is a data parallel programming language. So one that has had some we've certainly looked at it. And with that, I'd like to turn it over to Brad. I'm really looking forward to hearing this talk.
Thanks very much. All right, so good morning, and thanks for coming. As you heard, my name is Brad Chamberlain. I work at Cray. I'm going to be talking to you today about this language we're developing called Chapel, which is, as David said, a next-generation parallel programming language. And this is joint work with our academic colleagues at Caltech JPL. I just get to be the one to tell you about it today. So let me start out by telling you about the context for this work. This work is being done as part of what's called the HPCS project, which stands for High Productivity Computing Systems. So the P there has changed from performance, which is what it typically is in HPC, to productivity. And this is a program that DARPA started a while back and will go through the year 2010. The overall goal of this program is to increase productivity for high-end computing. So the observation is that high-end computing is sort of frustrating and hard, and what can we be doing to make it easier? And this program defines the term productivity to mean programmability with performance, with portability, with robustness. So these are sort of the 4 prongs of productivity that the program tries to address. And people participating in this program were required to turn out a result which would be revolutionary, not just sort of the next step of their product line. They had to sort of step off that evolutionary scale. And also has to be marketable to users beyond just the program sponsors. So the goal here is to generate something that will have wide spread effect, as opposed to something that just DARPA and other government agencies will be interested in and nobody else will be. We're currently in the middle of phase 2 of this program, or actually towards the end of phase 2 of this program. There are 3 vendors participating at this point, Cray, IBM, and Sun. We're about to go through a down select in the summer of 2006 to either 1 or 2 teams. And those teams will go on and build their systems for the year 2010. I'll talk a little bit more about that down select later on at the end of the talk. So Cray's effort in this HPCS program is called Cascade. That's the name of the project. And Cascade is essentially looking at parallel computing systems all the way across the system stack to see how they can be changed to impact productivity. So this includes new processor designs, new memory architectures, network designs, operating systems, runtime, compilers, tools, programming environments, and languages. Languages is where Chapel fits in, and Chapel stands roughly for the Cascade High Productivity Language. So that's what you'll be hearing about today. I'm not really going to spend any time today talking about the rest of the program, other than to just highlight a few of the architectural features of the Cascade machine that we're designing, because that'll help you understand some of the design decisions we've made for the language. So the Cascade machine will have a global shared address space. The network is a high radix, high bandwidth network. It has processors which can tolerate memory latencies of remote accesses, either through vectors or through multi-threading in hardware. And we think of this machine as being organized into locales. And you can think of a locale as sort of processing component with the memory that it can access cheaply because it's nearby. So this is sort of the unit of locality within the hardware. So when I go out and give talks about Chapel, one of the questions you get a lot in the HPC community, which is a community that's traditionally been burned by languages in the past, is, well, why are you bothering to develop a new language? Why waste your time? And this slide has a long answer, most of which I've grayed out. The short answer is that we believe that current parallel languages are lacking. And normally I would tell you why, and normally you'd be members of the HPC community, so you'd sort of go, yeah, that's true. But instead what I've done is I've introduced a slight detour here, where I'm going to talk to you a little bit about some of the parallel programming models that are out there, in case you're not familiar with them. And then I'll come back to that slide, and we'll go through the grayed out topic. OK, so this is my very quick introduction to parallel programming models. Then I'll talk to you about Chapel a bit. Then if time permits, we'll go through a sample computation in Chapel. And then I have some wrap-up slides at the end. OK, so parallel programming models. I'm only going to talk about models at a very high level. And in particular, talk about sort of these 3 distinctions that I think of. In the Chapel project, we came up with this term for fragmented programming models. These are models in which the programmer basically writes code thinking about their program on a processor-by-processor basis. So you're writing code that says, what should this processor do? And the idea being that you'll have many of these programs running, which cause all of the processors to sort of work together. So in doing this, you're going to take your data structures, you're going to break them up into little per-processor pieces, and you're going to take your control flow and break that up into little per-processor pieces as well. One of the main instances of this fragmented model, which is really the most common instance that almost everyone uses today, is called the SPMD model, or single program multiple data. The idea here is you're going to write one program and then just run multiple copies of that program. And to make it do actually something interesting, those programs are parameterized by what instance number you are. So you'll have branches on sort of if I'm processor 0, processor 1, so on and so forth. So most of the parallel language that people use today fit this SPMD model. That's the way people write code. In contrast with these fragmented SPMD models, we have this notion of a global view model. This is a model in which the programmer doesn't need to break everything down into a processor-by-processor basis. They write things in a more holistic fashion, and it's the compiler and the runtime's responsibility to actually take that whole description of the problem and break it down into per-processor pieces. And I should say that while we think of the compiler and the runtime as bearing most of this responsibility, the programmer can have hooks within the language to help guide the compiler and the runtime to the solution that they want. So let me make this a little bit more concrete, except that maybe I've turned off my remote. Or maybe I did something else. OK. Let's take a very simple data parallel example. Say we want to add 2,000 element vectors and assign the result to a third 1,000 element vector. Here I've replaced the number 1,000 by 6, it looks like, so it fits on my slide. In a global view model, you'd want to just say, OK, I've got these two vectors. They have 1,000 units. I want to add them together and assign. In a fragmented model, you would instead take those vectors and break them up into these per-processor pieces in terms of both the allocation and the control. So you're thinking in terms of those red lines indicate processor boundaries, and you're thinking about writing code that specifies what happens within any two of those red lines. And so the code using a pseudocode notation might look something like this. In the global view model, I've declared my problem size 1,000, and I've declared my arrays using that global problem size of 1,000. And then when I do my iteration, I also iterate over the global problem size of 1,000. And that's kind of intuitive and natural. In the fragmented model, instead, what I'm going to do, the changes are shown in blue, is I'm going to declare this variable local n. This is the number of elements that each processor owns. So that's going to be computed by taking n and dividing it by the number of processors. And then I declare both my arrays and my loop in terms of that local n rather than the global n. So this doesn't look that big of a deal, but this is about the simplest parallel program you could write. The other thing to notice here is that I've assumed that the n divides evenly by the number of processors. And if, in fact, that weren't true, or I didn't want to write that assumption into the code, I'd have to put in more effort to write a more general version of the code. OK, so again, this is a really simple program. Let's look at a slightly more interesting one. This is a problem where I say, apply a 3-point stencil to a vector. So I'm going to replace each interior element of the orange vector down here with the average of its two nearest neighbors from the blue vector. And so again, in the global view, I want to think about it in this sort of global terms. In the fragmented view, again, I'm going to chop those vectors up into per-processor pieces. But this time, because some of the data I need to access is not local, I'm going to allocate additional storage to cache non-local values on my processor. And so then I need to introduce communication in order to update those cached values, get copies of what my neighboring processors have. And only at that point can I actually do the computation itself. Basically, on each processor, I'll then replace orange elements with the average of their two neighboring blue elements. OK, so in terms of the code, this adds more complexity. As before, I chop up my problem size across the processors. But then I introduce some sort of communication here, which says, well, if I have a right neighbor, I need to exchange a piece of data with it. And if I have a left neighbor, I need to exchange a piece of data with it. And this is the code that I've actually been showing in this talk for over a year. A friend of mine gave a version of this talk recently, and he found a bug in this, which, in my mind, it sort of shows how the fragmented model is kind of frustrating. Does anybody see it offhand? I know you haven't had much time to look at this. OK, so the bug was this loop here. So I'm looping over. I'm saying all processors should loop over their local elements, doing this averaging step. But the problem is, because of my global view, I don't want to do the two endpoints. I'm looping from 2 to n minus 1 rather than 1 to n. I have the same problem here, where I need to do those global boundaries here as well. So what I needed to do is put in some additional variables which said, well, in this loop, what bounds should I loop over? And then depending on whether or not I have a right or left neighbor, I have to adjust those upper bounds. And these are the kind of details that the fragmented model just sort of forces on the programmer and which drive you crazy very quickly. This is why we prefer a global view. The other thing to note here is that the communication I've expressed here is proportional to sort of the dimension of the array you're operating on. So here, because we're working on vectors, we have to communicate with 2 neighbors. If you work on 2D arrays and they're distributed in both dimensions, you tend to have to communicate with your 8 nearest neighbors. In 3D, it's 27. So you sort of have this explosion of communication you have to express and do as you move to higher dimensional arrays. The one other thing I wanted to say here was that I've expressed all this communication in terms of sends and receives, which is a 2-sided message passing paradigm. There are many other paradigms that one could use for this, like co-arrays or one-sided communication or shared memory with synchronization. And that's really not the important thing. The important thing is that you as a programmer need to go in and sort of manage this communication by hand in these fragmented models. OK, so just to blow this example up a little bit more, this is that example we just saw, replacing my little send-receive pseudocode things with actual MPI calls. If you're not familiar with MPI, this is a library for message passing. It's pretty much the absolute dominant programming model for high-performance computing right now. Like I don't know the number, but I would guess over 95% of parallel codes probably are written in MPI. And the main thing to note here is that my sends and receives have kind of blossomed into these calls with many, many arguments to specify where's the data, how much is it, what type is it, who am I communicating with, what's the unique ID for this, and then things like error handling and stuff like that. So this is just to give you a flavor of what does MPI programming look like for even this very simple example. All right, let me give you one other example of these programming models. We've only looked at data parallel examples so far, but task parallel examples are also interesting. So, we all learned that quicksort is a divide and conquer algorithm. It sort of should be trivially parallelizable. So globally, I want to think about taking this quicksort, breaking it into 2 parallel tasks, each of which is broken into 2 parallel tasks, and so on and so forth. In a fragmented model, I would again need to decompose that across processors somehow. So here I've drawn red lines again to indicate processor boundaries, with the idea being that one processor will handle sort of all of the sorting work in any one of those areas. And if we look at the code for this, again, in the global view, I'd like to sort of not worry about the processors so much. So I'll say something like compute a pivot, and then in parallel do these 2 quicksort stages. That's what that co-begin terminology means. In the fragmented model, instead, I have to, again, sort of think about it from one processor's point of view. So I sort of have this recursion tree, which is overlaid on top of my processors. And I need to say, well, if I have a parent in that tree, let's receive some work to do from them. And then if I have a child, I'm going to compute a pivot, send half the work to my child, do the other half myself. If I don't have a child, I'm just going to do all the sorting myself. Then if I have a child, I'm going to receive their result back from them. And if I have a parent, I'll send the global result back to them. So again, there's sort of more work to be done here and more obfuscation in the algorithm in the fragmented model. OK, so here's a quick summary, at least showing the biases that I've just sort of shown to you. When you use these fragmented models, you tend to obfuscate the algorithms you're trying to write by putting lots and lots of per-processor management detail right in line with the computation. Now, if you're a scientific computing type of person, you've got a problem you want to solve, an algorithm you want to write. And all of these little details sort of make working on that problem, working on that algorithm, much more complicated. Because the parallelism for you is more of an acceleration mechanism. It's not sort of what you're getting paid to do necessarily. These models tend to also require you to write your code with the SPMD model in mind. And frankly, provide only a really blunt means of describing both parallelism and distributed data structures, which is, well, the parallelism is these programs running, and the distributed data structures are whatever data they allocate. What I've done here at the bottom is list a bunch of mostly parallel programming systems and broken them into roughly fragmented versus global view languages. And the main thing to note here is that almost all of the languages that are commonly used today are in this fragmented model. This is because they're easy to compile, frankly. But it's unfortunate because if you want to be productive, you'd really rather have more of a global view language. And there have been global view languages in the past. HPF was a very notorious one. ZPL, the one you heard I worked on at University of Washington. Sisal and Nestle, which were some functional languages. Cray had a dialect of MTA, a dialect of C and Fortran for their multi-threading architecture, which also had this global view nature. And the point is that none of these have really sort of escaped being, I guess, research languages or academic languages. They haven't ever made it into the mainstream, with the exception of HPF, which did but faltered and sort of is why a lot of people are grumpy about languages in our community today. Okay, so back to this, why develop a new language? As I said, we believe current parallel languages are lacking. In general, the biggest thing for me is that in general they tend to require this fragmentation of data structures and control structures. And in doing that, you fail to cleanly isolate your computation from various changes that you might want to make to it over time, such as how do you want to think of your virtual processors as being arranged? How do you want to decompose data across those processors? How do you want to communicate between those processors? What kind of data structures and memory layout do you want to use? Typically, anytime you change these things, your program has to change in major ways because you've embedded these details sort of throughout the structure of the program. Some other things which haven't come up in the past slides, most of the models we have today tend to support only a single type of parallelism well, either data parallelism or task parallelism, but not both. Usually, the other looks weird in any given language. They tend to fail to support a composition of parallelism. So you typically have a single level of parallelism, and then you're sort of out of luck if you have more parallel work you want to do within there. They tend to have very few data abstractions, things like distributed sparse arrays, graphs, or hash tables. These are things that the scientific community wants to use all the time, and yet they always have to grow them themselves by hand. And in addition, there's just a lack of broad market language features, things that young students coming out of school are used to in languages like Java and MATLAB, but then they're thrust into sort of this Fortran plus MPI or C plus MPI world, and they just think they've been thrown back to the Stone Age, basically. All right, so those are our reasons for doing Chapel. Let me now tell you a little bit about Chapel. Yeah?
A very brief summary of why the other languages in the global view faltered.
Yeah. So I sort of skipped over OpenMP. OpenMP is actually a system which is still in use today, but it tends to assume that you have shared memory between all of your processing elements. And so what's been found in practice is that OpenMP is good for talking about sort of nodes of sort of a say a 4-processor cluster or something like that for those 4 processor nodes, but not so good across the cluster itself. So an SGI shared memory machine is one of the few places you'll see OpenMP sort of scaling to hundreds or thousands of processors. High-performance Fortran, depending on who you talk to. So high-performance Fortran was this really large effort. Academia and the government really threw a lot of weight behind this. Corporations spent a lot of time on it. And why it faltered depends a lot on who you talk to. In grad school, I used to argue a lot that it faltered because it didn't have a good performance model. So you as a programmer wrote code, and the language gave you no guarantees as to how that was going to be implemented. So you're sort of casting your hope to the wind. And then maybe you got something working well with one compiler. You went to another compiler, and maybe it did something completely different. Other people will argue that it failed because it was called high performance, and when version 1.0 shipped, the performance wasn't that good, and people just immediately said, oh, well, forget that, and didn't have the patience to wait for it to mature. Others would say that it didn't go far enough in providing abstractions. It had a few abstractions, but not so much that you could do sort of, for example, sparse distributed codes very easily and things like that. And therefore, it was too incremental, essentially. ZPL, I'm biased on. I'm probably not the right person to ask. But in ZPL, we never really sort of broke out of an academic setting. We sort of did really nice academic work. We weren't sort of maybe as entrepreneurial as other groups. And we're also dealing with the fact that everyone was disgruntled about HPF. And so while I think we did nice work, we never sort of made it into a product or had collaborations with a vendor or anything like that. So it remained sort of an academic work. With functional languages, I think part of what was working against them is just that they were functional by nature. You're trying to sell to an industry that's very imperatively based. Cray MTAC and Fortran was great, but it depended very much on the Cray MTA architecture. MATLAB I have up here because a lot of people in this community really want a parallel MATLAB. And I think one of the things they like about it is that they don't have to think about the processors. Well, it's a sequential language. Of course, they don't have to. You could also put Java and C and things like that there. So that's why I think. I mean, it's different for every language, obviously.
Where would you put Google's MapReduce on this space? Would you say it's not a language, it's a shell or something? Or would you say that it's functional and therefore you can't sell into an imperative thing? Or?
So I have to admit, I'm not that familiar with.
That's a very special purpose functional language.
Yeah.
You can do.
So it's just not playing in this space.
Would you call it global view? Like, does it abstract the processor space away from the sort of thing you're trying to describe? So that would make it a global view.
Provides map and reduce operations.
Okay.
Apply a map operation.
Over distributed data structure. Okay. Yeah, so that would make it, I would say, a global view. Although maybe not the most general purpose one. I'm not that familiar.
Can you characterize X10 as the work at IBM?
Yeah. So X10, I should say that the other two vendors are also developing languages. IBM's is called X10, Sun's is called Fortress. X10 tries to straddle this space in an interesting way. X10 has this notion of a place, which you could think of as being like our locale. It's sort of an area where you can do computation and have some local memory. And when I read X10, a lot of what I see looks very fragmented in nature. You sort of write code for these places, and the places communicate with each other using these async operations, which are kind of like message passing. And that has a very fragmented feel to it. But in some of their talks, I've heard IBM talk about, well, but you could write code that's just one place, written for one place, and then spread that place across multiple processors. And so the implication there is, well, you could use it in a global view mode where you sort of only talk about one place and rely on the compiler, I guess, to sort of spread it across multiple physical processors. For me, though, that's not very compelling. I mean, they obviously have built a lot into the language, assuming you're going to use this fragmented mode. So I'm guessing that the global view mode is not going to be as good performance. And there's something else.
All of blue gene, for example,
I mean, I think that's the idea. I don't think they're there yet, but
as a single locale, or is
as a small place, yeah, right.
So they would run a single place on all 130,000 processors of the biggest blue gene.
That would be the idea. But
another arrow in their quiver. I think what they're really trying to do is come up with a programming model that will work for clustered SSPs, which is what IBM sees as their future. So I think you'll see, something more like 1,000 16 processor things with the global view within the 16 processor thing, but explicit fragmentation among the SSPs.
Yeah, and a lot of people do this today with MPI across and then OpenMP. Yeah. To me, the problem with this is that they sort of sell it as, oh yeah, you can do one place or multiple places, but it's not as though there's a gentle ramp in making that transition. It's like once you decide you're going to break up your one place, I suspect there's a lot of work there. And so to me, that isn't sort of the best sell. But yeah, so they're trying to kind of play both games, I would say. Any other questions? OK, so let's talk about Chapel a little bit. So Chapel, as I said, stands for the Cascade High Productivity Language. The overall goal, and I'll attribute this to my ex-manager, Wendy, who's sitting in the audience, is to solve the parallel programming problem. And I should say, in saying that this is our goal, that's not to say we necessarily believe we're going to do it, but it's what we're setting out to do. Wendy has given me many, many hours of grief over this goal. So I had to keep it up here just for her. What I think about it as meaning is we want to be able to simplify the creation of parallel programs. You should be able to sit down at a parallel machine and get a code up and running pretty quickly. It shouldn't be sort of this days-long process just to get your first program that runs across multiple processors or uses the memory of multiple processors up and running. Then what you want to be able to do is take that code that you've written pretty quickly and be able to evolve it into more of a performance-oriented code, more of a production-grade code, without completely abandoning the language, without completely rewriting everything from scratch. And the third goal I'll say here is to emphasize generality. So what a lot of languages do, including ZPL, the one I worked on in graduate school, is to sort of carve off, well, this is the area we're going to attack. And once you want to do something outside that area, you're kind of stuck. And so in designing Chapel, we've designed it very much to be a very general parallel language. There are four main language technologies which have motivated our design, and I'm going to use these to sort of structure the way I talk about most of the features in the language. The first is multi-threaded parallel programming, and I'll spend the most time on this one. The second is locality-aware programming, so being aware of where things are on the machine. The third is object-oriented programming, and the fourth is generic programming and type inference. And I'll spend more time on the earlier topics and less on the later ones, partially to reflect my own interests and, well, I guess only to reflect my own interests. So first of all, multi-threaded parallel programming. When you think about this, you should think of this in terms of supporting language concepts which virtualize threads. So we don't want you to have to go out and write a bunch of sort of fork off a thread and then join back together with that thread. Rather, we'd like to supply a number of higher-level concepts which result in multi-threaded execution, where you as the user aren't explicitly naming and talking about threads. So we have abstractions here to do this, both for data and task parallelism, and I'll talk about these in much more length on the next few slides. In addition, as I said, we want to be able to compose parallelism, so you should be able to do parallel work within another piece of parallel work. rather than having only a single level of parallelism. And we want to support this global view of computations and data structures, which I just talked about in length. Okay, so let's talk about data parallelism first. Domains are sort of one of the key concepts here for data parallelism. And you can think of a domain as essentially a language concept, a first-class language concept, which represents an index set, okay, a set of indices. And you can think of this as sort of something which can specify the size and shape of arrays. Typically in our languages, arrays and their index sets are sort of all declared together. Here we've factored the index set part away from the array to talk about it separately. And I'll show more examples of this on subsequent slides. These domains support both sequential and parallel iteration, and they could potentially be decomposed across locales. So you can have a single array or domain that's distributed across multiple processors, essentially. I'll talk about three main classes of domains today. The first are arithmetic domains. These are like the arrays you're most used to, probably. The indices are Cartesian tuples, like rows and columns and things like that. So these tend to represent rectilinear, multidimensional data spaces, and they can be strided in any dimension or sparse in any dimension. The second type of domain is an indefinite domain. These are domains in which the indices are essentially hash keys. So you can index into the array using strings or object references or things like that. You can think of these as being like associative arrays, essentially, or hash tables. The third class of domains are opaque domains, and these are ones in which the indices are anonymous. So you can think of this as you've got a bunch of indices floating out in space. You don't have any particularly good names for them based on your problem that you're trying to express. So therefore, they're just sort of anonymous. And you can think of this as being useful for describing sets or graph-based computation, essentially, where there's not sort of this rigid structure. As I said, domains are Chapel's fundamental concept for data parallelism. And if you're familiar with the ZPL language, a lot of these domain concepts come out of the region concept that existed in that language. So here's a really, really simple domain declaration. I declare a couple of integers, m and n, to be 4 and 8. And then I declare this domain D, which I say is a two-dimensional domain, which puts it into the arithmetic domain class. And I say that it goes from 1 to m and 1 to n. So that gives me this little 4 by 8 set of indices. And again, this looks a lot like an array, but it's not really an array. It's just sort of the indices which you might use to describe an array. I can declare a second domain here called D inner. I declare this to actually be, rather than a two-dimensional domain, I say it's a subdomain of D. And what that means is that all of its indices are also going to be indices of D. And I say that it's going to be from 2 to m-1 and 2 to n-1. So that gives me sort of the indices that are in the inner portion of D. Now, having created these domains, I can use them for a bunch of different things. First of all, I'm going to use them to declare arrays. So at the top there, I declare arrays A and B, which I say are their size and shape are defined by domain D. And for every index in domain D, I'd like to allocate a floating point value. So this gives me these 4 by 8 arrays of floating point values. You can use domains to do subarray references, sort of a rich slicing notation. So I can say A sub D inner equals B sub D inner. That takes the slices of A and B, which are described by the D inner domain, and assigns those, leaving the boundaries untouched. I can also do sequential and parallel iteration using for and for all loops. I guess I do have to use the pointer. Sorry. Or no, I can stand over here. Or will the camera hate me? I should use the pointer? Rats. I have no steadiness in my hand. OK, so sequential iteration says for all indices I, j in D inner, do something with A, I, j, for example. And so that's just going to iterate over the indices in the inner portion in sequential order. Parallel iteration is similar. For all I, j in D inner, do something with A of I, j. And I should say the two forms I have here, one just sort of decomposes the indices into integers, essentially. And the other one keeps it as one tuple. So we support tuples in language, and this is just tuple indexing of that array. So the parallel version, I just replace the for with the for all. Or there's also an expression level parallel iteration here, which just uses a different syntax but is the same thing in an expression context. The last use of domains I'll talk about here is for array reallocation. If you reassign the index set that a domain represents, that results in a reallocation of the arrays that are declared over that domain. So here, for example, I'm doubling the size of D in each dimension. And that's going to cause A and B to be reallocated to be twice as big in each dimension as well. Now, this example may seem a little bit funny, and it probably is. You may not double the size of your two-dimensional arrays very often. But one of the places where I think this has real good application is in the case of sparse domains, where over time your sparse computation may fill in. You're going to want to add in more indices over time and ideally have your arrays sort of track those new indices rather than having to go and reallocate everything by hand. OK, so some other arithmetic domains This first one, D2, is actually the same domain but declared using tuple style notation. And this is of interest to me because I think writing rank-independent codes seems to be kind of a pet project of mine. And so this would be a slightly more rank-independent way of writing this. The second one is a strided domain where I take D and I stride it by 2 in the first dimension and 3 in the second dimension. That'll still result in a dense allocation, but logically it allows me to index into things in a strided manner. And the last one is a sparse domain where I, again, take a subset of D defined by some index list and basically just capture an arbitrary sparse subset of indices from D. One of the things I think is really interesting about these domains is you can think of there as being this hierarchy of domains much as there's a class hierarchy in object-oriented languages. So if you've been following the declarations I've been doing, I said that D and D2 were both two-dimensional domains. And then I made D-inner and my strided domain and my sparse domain all be subdomains of D. And what that says, again, is that each of these subdomains contains indices that are only contained within the parent domain. There's also this set of index types in the language. So an index 2, for example, is just a two-dimensional index, a row, column, or something of that sort. And then when I say something like index of D, that says, well, this, if I declare a variable it's an index of D, this isn't just a two-dimensional index. It's also an index that happens to be in the D domain. So the nice thing here is that when you have an expression like this for all loop, for all ij and D-inner, what the compiler is going to do is say, well, ij is an index of the D-inner domain, because that's what I'm iterating over. And then when I use it to index into A, which was defined over D, I can say, oh, well, this index of the D-inner domain, that's a subset of the indices within the D domain. An index within the D domain, that's the domain we declared A over. So by definition, this is going to be in bounds. I don't have to do any runtime bounds checking in order to make sure that's legal. And I find this really attractive, both as a compiler writer in terms of doing bounds checking optimizations, and as a programmer who likes to write sort of code that's descriptive. It's sort of nice to say, this thing is guaranteed to be an index of D as opposed to just a general two-dimensional index. All right, so moving on out of the arithmetic domains, indefinite domains are these ones that are kind of have this hash table or dictionary type of functionality. Here I declare a domain called people. This is a domain over strings. And then I declare two arrays over it. Age, which is an array over people of integers, and birth date, which is an array over people of strings. And I can say things like, the age of John is 60, and the birth date of John is December 11th, 1943. And this will cause that data to be stored into the age and birth date arrays. I can then compute over these just as I could in the arithmetic domains. I can say for all person in people, if the birth date of the person is today, then the age of the person plus equals 1. And as before, sort of the picture is that you've got this domain, which is just the set of indices which are used to describe this data structure, and then arrays which follow that domain in terms of their size and shape. And the third category of domain is these opaque domains. Again, these are used to describe set or graph-based data structures. And so I say, for example, give me an opaque domain named vertices. And then because these have these anonymous indices, I can just say, the way you get them, because you don't have a way of really naming them, is you say, give me a new index in the vertices domain. So I've done this 5 times here. I end up with 5 indices. Again, if I declare arrays over this indefinite domain, I end up with a data element per index here. So I sort of have these 5 floating point values floating out in space for each of my 2 arrays there. This is kind of an abstract example. Let me make a slightly more concrete one. Let's say I were to declare 2 arrays left and right, which are arrays over my vertices, where at each element I store an index into that vertex domain. I also store a variable root, which is an index into the vertex domain. And then I can write code like root gets a new vertex, and left of root gets a new vertex, and so on and so forth. And conceptually what I'm doing is building up this binary tree here, and the code sort of reflects that. What's really going on is that I've declared this domain of vertices, and I have these 2 arrays left and right, which are tracking the domain as it changes. And I've basically set these up to store indices back into the domain. So in a sense, you can think of them as almost being like a pointer-based data structure. I think the user is probably going to tend to think of it more in this conceptual model than in this model. OK, so that was a bunch of stuff on domains and data parallelism. Moving now into the task parallelism features of the language, we have a notion of co-begins in the language. This is a way of asserting that 2 statements may be run in parallel. So we actually saw this in the pseudocode for my quicksort before, where you compute a pivot, and then you say, these 2 quicksort calls can actually happen completely in parallel. They don't need to be 2 instances of the same task. You could also do compute task A and compute task B, where those are very different things in parallel. We have a notion in the language of atomic sections. This is a way of saying that all of this code should execute as though it was done at the same time simultaneously with respect to any other thread's view of it. So here, for example, I have a doubly linked list insertion. That's something that you don't want someone coming in partway through and mucking with those same pointers. So we wrap it with an atomic section to say all 4 of these assignments should happen as though they happen simultaneously. And the last feature I'm going to briefly mention here today is a notion of synchronization and single assignment variables. These are variables which have various semantics as to whether they can be read or written. And they typically have a notion of being sort of full or empty. So if something's empty, you can't read it. Once you store into it, that sets it to full. Depending on how you set it up, someone else may or may not be able to rewrite into it until it's been emptied again. This is very similar to a concept that was in the Cray MTA dialects of C and Fortran. And we're taking those ideas and putting them into Chapel as well. And this would be the main way that when you set up tasks using these co-begins, that you would have them synchronize with one another.
Is there any notion of restricting the variables I can touch when I do something like co-begin?
That is a good question. So currently there's not. Currently within the co-begin, you can do pretty much anything. So you can do race conditions, you can hurt yourself, yeah. And that's kind of by design. There's the sense that once you start putting restrictions on things, there may be things you can't write or can't write as easily. And so we've taken the approach of letting people shoot themselves in the foot. But there is sort of this concern that, well, is that really going to make people more productive? And you might imagine a co-begin in which you sort of say, well, this branch can only touch these variables, this branch can touch these variables, and assert some sort of safety that they're not going to interfere with each other. I think that remains to be seen whether we end up doing something more along those lines.
You guys thought about using the type system to take advantage of that, to declare a variable? Like in C, you can declare something as const, you can declare something as basically not modifiable by any other thread.
Right. We haven't done anything along those lines yet. But I think that you could imagine certainly introducing something like that with this might make things much more tractable. Microsoft Research in Cambridge did some nice work on atomic sections in Haskell, which used the type system to sort of prove whether or not things could go into an atomic block or needed to be accessed within an atomic block. And I think that was a really attractive work as well that we need to keep looking at.
Yeah, I think one of the really interesting open questions here is if you have atomic and the functional language like Haskell or single assignment and declared properly, right? Is that enough? You know, is that all you need, or do you need more stuff? And because if that's all you need, the composability story looks pretty good. So, you know, if you start adding locks or other things, it gets a little hairier.
Right.
So it's a really good question, I think.
Well, that's right. What happens if you use an atomic section and inside of it you make references or stores to sync and single assignment variables? Because the essence of atomic is this sort of like a transaction that either happens all or none.
Right.
And how do you roll back a single assignment?
I suppose you don't commit that single assignment until after you leave the atomic block. So,
Okay, so anybody who's trying to look at state has to be blocked until...
right. So
Okay.
I mean, the way these atomic blocks tend to be, right, so the way these tend to be implemented is you do the modifications sort of off on side data structures, and then at the end you see, can I swap all this state in and has nothing I've read changed? And I imagine you could do the same thing with single assignment variables, although I have to admit I haven't thought very hard.
In fact, they have to be atomic. And being composable with atomic.
Yes. That may be true. I have to admit I have not thought very much about this interaction.
It has to be as if at the end of all of this.
Yeah.
So one of the issues with software transactional memory has always been this question about what happens when you do things like system calls in the middle of an atomic. Do you disallow that? What are the semantics?
That's a good question. I promised David I wouldn't throw questions at him. So David Callahan was one of the architects of language, and
Now he's going to do it.
I'm tempted to do it. I guess I don't know offhand. It seems as though you would probably want to restrict system calls from being in atomics because of the fact that you can't really do them on the side and roll them back. I know the Haskell work they did things like that, and also sort of had peculiarities about what you could do with exceptions within atomic blocks. I guess in my stammering, what I'm saying is I'm not the expert at the task parallel features in the language, and so I don't know offhand sort of what the exact restrictions would be there.
The solution in the Haskell framework is very elegant. Basically, any system call is viewed as an I/O reference, and that can't be an argument to the that turns transactional things into I/O things. So it's a kind of a cool way to do it. You just say no is one way to go. Right. There's some others you could do, but the things that are pointed out in that paper, in that Peapod paper, need to be watched carefully. It's a nice solution to that problem, and you have to come up with one at least as good, I think, if you're going to do that.
My gut reaction to these kind of questions is to disallow things that are going to be extremely hard to sort of do right or do efficiently. So that sort of disallowing the system calls might be better than sort of allowing them and then going to great lengths in order to sort of make them all work. But that's just sort of a gut reaction. I don't know if all my team members would agree with me on that. OK, so moving on to the second theme of the language, locality-aware programming. This is this idea that we sort of want to know where data is and where computation takes place. And I mentioned at the top of the talk that in the architecture we have this notion of a locale, which is sort of a unit of machine storage and processing. There's also that notion in the language as well. There's an opaque type called a locale, which allows the programmer to refer to the processing elements in the system, essentially. So as a user of the language, when you start executing your program, you can specify the number of locales you want to run on the command line. So for example, here I'm running a program with 8 locales. Whenever you start up your program, you're going to have a built-in array of locales that's provided for you by the language, which is essentially just sort of those 8, in this example, those 8 locales that you started running on. And that gives you sort of this seed to talk about the processing resources. But then you can take those locales and put them into different data structures that sort of match your way of thinking about them better. So for example, if you want to think of those 8 locales as being sort of a 2-dimensional 2x4 set of locales, then you can take that array of locales and reshape it to be this 2-dimensional array of locales that fits the way you want to think about them. Or you could also take them and carve them into 2 separate chunks and say, well, I'd like sort of this set of 2 locales to work on task A and the set of 6 locales to work on task B. I'd like to sort of separate them into 2 arrays of locales in that manner.
So in that final example, is there any semantics that suggests that the two locales don't overlap?
No, so you could actually have one locale that belonged to both of these groups if you wanted to.
But OK.
You can imagine that if you could prove that 2 arrays of locales were disjoint, that might be really beneficial information from sort of an implementation optimization point of view. But the language doesn't restrict you from including the same locale in multiple ones. Our execution model here is going to be multi-threaded. So you should think of each of those locales as having multiple threads of control. So the fact that a locale belongs to 2 of these sets shouldn't be worrisome because it can just be running threads from either one of those tasks, for example.
So in some sense, you're moving away from this global view that you were promoting before.
That's right. So there is this tension between you want the global view for convenience, but at some point you may want to start talking about processors or locales in order to start optimizing for performance more. And so the question is, how do you do that in a way that allows you to sort of gradually ramp from sort of a pure global view where you're not concerned about locales at all to sort of a mixed mode where you're writing in the global view, but you're still thinking about or telling the compiler how to map it to processors, and we'll see that in the next slide, to sort of a purely fragmented model where you're really programming sort of processor by processor. And our goal is to stay in those top 2 categories as much as possible and force you to fall back to the 3rd category only when absolutely necessary.
Is it possible to have this be a logical concept where you have one level where you just define a bunch of locales, and then a second sort of structure where you figure out the mapping between those locales and the actual hardware?
Right, so you're talking about, rather than having sort of a one-to-one correspondence between those locales and hardware resources, have sort of multiple virtual software locales mapping to one hardware locale. You certainly could do that.
A set of hardware locales.
Or a set of hardware locales.
Well, in a simple-minded sense, you can think about taking a database and partitioning it into n parts, and then you just say, OK, it's partitioned. We'll map it to the processors modulo the number of physical processors.
Right. So this question of mapping virtual locales to physical locales is an interesting one. I don't think we're opposed in language to having multiple of these software locales mapping to a single hardware locale. In my use, I tend to think of them one-to-one because I get uncomfortable with too much virtualization. But I don't think there's anything currently in the language spec or in the implementation which would prevent you from doing that, I guess, is how I would address that. Yeah?
So I get 2 levels of locality, essentially, local and remote?
Yes.
Are you worried that when multi-core and many-core comes along, you're going to need more than that?
Yeah, that's a good question. You could even imagine doing that on current clusters where you have sort of processors that are near each other and farther from each other. And I've sort of wondered about whether you could have sort of an array of locales where sort of the first level of the array meant it was more distant and the second level meant they were more close. For now, though, we're sort of only worrying about remote versus local. But I think you're right. That would be an interesting thing to pursue when those architectures, well, I guess they're already prevalent. When you start caring about that more.
Let me make a point of possible clarification. A locale is in no way a processor. It's an address space. It's a neighborhood. Think of it that way. So if Minicore gives you one neighborhood per die, you're fine. It's only when you have internal locality on chip or something, and also, yeah, right.
But we
It's to be seen what those things look like.
Absolutely.
But we typically wouldn't take one of these locales and break it across sort of processors that were reasonably distant. So we wouldn't sort of do the IBM thing of having one locale that spans the whole machine, for example. Okay, so here's a little bit about how we use these locales. The first is that locales can be used to distribute domains. So in this example, I've taken the same domain declaration that we saw before for domain D, and I've added in this additional information which says distribute this in a block 2 manner to comp grid, which is my two-dimensional locale view there. And so what this means is block 2 is, for example, maybe a built-in library distribution, and it says to block both dimensions of the domain. So I sort of end up with this 8 locale partitioning here. And what that means is each locale is going to own that piece of the domain. In addition, this implies a partitioning of the arrays that were declared in terms of that locale. These distributions on these domains specify not only a mapping of indices to locales, but we also think of them as specifying how each locale should store its indices locally and how it should store its array elements locally. So you can imagine, for example, for a sparse domain, that this distribution would specify whether local to each locale, the sparse indices were stored using compressed sparse row storage or some other sparse storage format. Distributions in the language are implemented as a class hierarchy. And you can think of it as Chapel providing a number of standard distributions as part of a class library, essentially. But users can also write their own, either from scratch or by subclassing off that class hierarchy and making modifications, for example, to the standard block to fit some particular feature of their algorithm. I should say that these user-defined data distributions, I think, are one of our biggest research challenges. Other languages have typically built in a fixed number of distributions, and if it didn't suit your needs, you were kind of out of luck. We really want to make it users able to write their own distributions, but this is a really hard challenge without sacrificing performance in a big way. So we also use locales to distribute computation. This is typically done with the on keyword, and we can say things like, in this co-begin that I had before, I've now appended the work with this on indicator, which says, compute task A on the task A locales and compute task B on the task B locales. And that's just an indicator of where those computations should run. You can also use on in more of a data-driven manner. So here I've actually referenced locales with the on clause. You can also reference just a data item, and it says run it on whichever locale owns that data item. So here I'm doing some weird assignment from B to A using some weird indexing scheme, and I'm saying do this on the locale that owns the B element. So for example, if I was computing this B element assigned to that A element, the locale which is going to perform this computation is the one that owns the B element, or F in this distribution. Okay, the third theme of the language, one I'm not going to spend very much time on, is object-oriented programming. I'm probably preaching more to the choir here than I am when I'm talking to the HPC community. Object-oriented programming has obviously proven to be very good in helping to manage program complexity. It's a way of encapsulating data and code that's related to one another. It facilitates reuse and separates common interfaces from specific implementations. In Chapel, we have two notions of objects, both sort of what I'd call a traditional or reference-based object, like in Java, where you pass and assign things by reference, as well as value classes where you pass and assign things more by value or by name. In designing Chapel, we've tried very hard not to make it a pure object-oriented language. There are a couple of reasons for this. One is sort of the performance of sort of a very pure object-oriented language where integers are classes, for example. And the second is that we want to make this language very accessible to sort of the traditional HPC community, who uses predominantly sort of C and Fortran still. We'd like you to be able to use Chapel without sort of, for a lot of them, you tell them it's an object-oriented language, and they say, oh, well, you know, that's for young kids, and I don't know how to do all that, and I have to think about things completely differently if I want to do that. And we'd like you to sort of be able to use this in imperative style if that's your preference, but also to be able to use an object-oriented style if that's your preference. The one exception to this is that several of the more advanced language features we tend to express using classes. So if you want to write your own data distribution for a domain, for example, as I said before, we represent that using a class hierarchy because it's a really nice way to say, here are the interfaces that you need to define and also to get some reuse. So if you were a Fortran 77 programmer who wanted to write your own data distribution, at that point you might need to bite the bullet and at least learn how to fill out sort of a very specific class template. Yes, question?
So one of the things about object-oriented programming is that there certainly tends to be more of an emphasis on dynamic memory allocation. Objects become things in the heap, and then once you have all these objects in the heap in a global heap, you have this issue of sharing. A particular object in the heap. Who can modify it? Who owns it? And it doesn't seem like you have mechanisms that allow those objects to be partitioned in any way. The arrays can be partitioned, but you didn't say much about partitioning.
Yeah. So if you just have a bunch of objects kind of floating out in space, then by and large, there's no way to talk about partitioning them as an aggregate. I mean, you could steer the allocation of each one by saying, on this locale, new object, or things like that. But that's obviously pretty low level and frustrating. I think if you really wanted to work with a large collection of objects, you probably would create an array of those objects, such as, for example, the opaque domain and array concept, where you have sort of these objects floating around in space, or maybe even specify relationships between them. So you would imagine, for example, that a distribution on an opaque domain would be more like a graph partitioning algorithm. And it might say, OK, well, I've built in some knowledge about sort of what the semantics of my objects are and how they're interrelated to one another. And while I might like to think of them as just this cloud of objects, if I went to the trouble of saying it's an opaque array of objects, then I sort of have this ability to also talk about their aggregate distribution. And that's kind of the way I would imagine something like that working in the language.
So one of the things, though, is that somebody might have a reference to one of those objects. So it seems like it'd be very hard to do any kind of static analysis to determine whether a particular object can only be modified by on a particular locale.
Yeah, I think that's definitely true. So currently, I would love for someone here to say this is not a problem. So currently in the language spec, we have a notion of garbage collection being one of the features of the language. Primarily because of this kind of problem. It gets really hard to manage sort of which of those objects have been allocated, where have references been captured, things like that. And so also garbage collection is obviously shown to be incredibly productive in the sequential computing world. So we have this notion of garbage collection as a feature of the language, yet it's a feature that we as a research team have not spent any time looking at yet and are very concerned about sort of how do you do garbage collection on the scale of thousands or tens of thousands of processors and even more threads. For me personally, it's a big concern. It's also not my background, so I feel really woefully unprepared to sort of tackle that problem. But that's sort of how we would imagine dealing with that kind of problem. I suspect there are a lot of easy cases where you could statically determine, OK, this is a big array of objects, and there are no references captured to it, and therefore you don't really have much of a problem. But as you say, as soon as you've captured a reference to one of the elements in that array, you've potentially created this really hard problem to solve. I don't have a really good answer there. I'm hoping we have a parallel garbage collection.
Good thing to talk about later on.
OK, great. All right. The fourth theme of the language is this notion of generic programming and latent types. So the ability to sort of write code that is more flexible in terms of type than what we're used to in C, for example. We have a number of ways of doing this. The first example I have here is a stat class where the first thing I've declared in it is a type T. This sort of says, well, there's some type T that's used to parameterize this class. I'm not going to specify what it is here. You can think of this as a lot like a C++ template, for example. And then I can use that type T to do things like allocate data within the class or specify what its methods return, things like that. We also have this notion of sort of what I call a type query variable. If I write a function like copy n elements, takes in a data array whose domain I don't really know and don't really care about. But let's call it D for the purpose of this function. And the data stored within that array is, again, a type I don't really know. Let's call it T, though. And then I can use those identifiers later on. So I can say, well, this function returns an array over domain D, also of type T. I can use them to declare local variables, things like that. This is a little bit sugary. It's very similar to these type variables, of course. But I think it's really nice from a productivity standpoint. And the last example is, in many cases, you can just write your code sort of leaving the types off altogether. They'll typically be inferred, in the case of this parameter, from call sites, in the case of this variable, from the initializer that's assigned into it. And so here the idea is you want to be able to write code and leave off types as people are used to in scripting languages. I should say that all of these concepts you shouldn't think of as resulting in a lot of runtime dynamic checks and dispatch and things like that. Most of these are more in sort of the do analysis at compile time, stamp out multiple copies of it, use the right copy for each call site. So it's more a convenience for the programmer to just not have to write code multiple times themselves, but it doesn't result in a lot of dynamic overhead. At least that's the goal. This is a laundry list of other Chapel features. We have notions of tuples and type selects. That's sort of a safe way of switching over type. We have sequences and user-defined iterators. We have notion of reductions and scans, which are parallel prefix operators in the language, including the ability for the user to write their own reductions and scans. As far as function calls go, we have notions of default arguments and name-based argument passing. We have overloading of functions and operators, currying of function calls. We have a notion of module for sort of large code namespace management. Interoperability with other languages is a key feature because there's a lot of code out there that people don't want to rewrite from scratch, but you do want to interface with it. And as I mentioned, garbage collection. OK, so I think I have a few more minutes. So we'll go through an example computation. I normally give my audience a choice here of which computation they want to see, but I'm going to guide your choice towards the fast multipole method, which is one of my favorites. So this is a code which I became interested in because a previous DARPA program, which was very interested in sort of data-intensive computation, had sort of identified this as a really interesting computation. So what I did was download their implementation, which was a sequential C or Fortran implementation, I think. And I started wading through the code as well as the documentation. And I just couldn't figure out at all what it was trying to do. It was really frustrating. And then I found out that the guy who wrote the code was a Boeing engineer. So I went over and talked to him. We drew some pictures on the whiteboard. And I came away saying, oh, well, this is really easy. It's just that C and Fortran are really bad languages for expressing it. So I'm going to walk you through at least a little bit of this. What I'm doing here is declaring two sorry, I'm terrible with pointers. Declaring two arrays here, outer signature function and inner signature function. And these are sort of these arrays of arrays of arrays of arrays of complexes. All right, so let me walk you through what each of these arrays is. The first one is this levels array.
Could you just say something about what the fast multiple method is trying
to do? Oh, sorry. What is the fast multiple method trying to do? The way Boeing uses it is essentially to figure out sort of radar signatures of planes, I believe. It's sort of, you can think of it as like an n-body style algorithm, where you want to say, what are the impacts of these components on one another? And things do drop off in space, as they do in sort of galaxy simulations and such. And that's sort of about the extent of my knowledge of it. You want to say something more, Burton?
I mean, it first appeared in those kinds of problems, in n-body problems like gravitation or whatever. Whereas the usual Barnes-Hut sort of approach says, if it's nearby, I'll take it into account. If it's far away, I'll ignore it, or something like that. What this says is, well, depending on how far it is away, I'll represent it by a point or by something more fancy, like a dipole or a quadrupole or whatever. So essentially what you do is you take whole neighborhoods and represent them in terms of what are called multipole expansions of those things, which tell you sort of what their attractive, repulsive makeup is at sort of medium range. This is technology that is actually the fastest technology available for solving those problems. And the best n-body codes there are combinations of Barnes-Hut type thing and this technology. Boeing applied it to radar signature for the first time, I think, although they didn't do the research, but they were the first people to write the code. So.
Okay. Are you going to be available to accompany me on a tour as I go and give this talk around?
Whatever.
It's always helpful to have Burton in the audience. OK, so we've got this big array of arrays thing. This first one is a 1D array just over the levels of the hierarchy. So I have sort of the finest level and the coarsest level and levels in between. And you notice that I'm using this level in levels notation here, which is, if you remember my for all expression, and the reason I do that is because I'm going to use that level value, sort of what level are we currently at, as a parameterization for my other arrays. OK, the next array is essentially a set of 3D arrays of sparse elements per level. So, for example, all of these white elements here are maybe, this is my pentagonal plane. are all of the elements that are present at the finest level. At the coarsest level, maybe I have all of the elements present. And because the elements that are present at each level are a function of that level, that's why I make this basically a function of the level of the hierarchy we're currently in. Now, each of those elements is another array. It's a 2D discretization of a spherical function. And the discretization varies with the level. So at the finer levels of the hierarchy, you can use a coarser discretization. And at the coarser levels of the hierarchy, you can use a finer discretization. So again, because the sizes of these 2D arrays are parameterized by the level of the hierarchy, again, that domain is parameterized by level. And finally, each of those elements is a 3-element vector, where each of those values stored there is a complex number. Okay? So an array of arrays. But if you think about this in C or Fortran, well, C in particular, it's all sort of a bunch of one-dimensional arrays that are maybe dynamically allocated and indexed into sort of by hand in order to get all of these different kinds of indexing. And it's just a complete mess. You lose all sort of notion of what's going on here. Now, I've obviously done a bunch of declarations to get these different domains, levels, sparse cubes, signature functions, and so on. Those are sort of more or less laid out here. I'm not going to walk through those in detail, but it's more or less the same concepts we've been seeing. And if it makes sense for you guys, I can give you a copy of the slides and you can look at it some more. So here's this computation which is done. This is sort of the hardest of the different stages of the computation. It's called the outer to inner translation. And essentially what happens is each element at any level in the hierarchy is replaced by some function of their nearby neighbors in sort of a 6 by 6 by 6 area. And again, I probably don't have the time to walk you through this in detail, but the coarse structure here, as you can see, I'm iterating over all my levels by -1, so from the coarsest down to the finest. And then at each level, I say for all cubes at that level, and then for all siblings in that cube in that 6 by 6 by 6 region, compute this translation table, which is itself one of these large discretizations of spherical functions of 3-element things of complexes. And then I say the inner signature function plus equals the outer signature function times the translation table. These are all large element-wise operations taking place over these 2-dimensional tables of 3-array vectors of complex numbers. Okay, so this is the way sort of these computations end up looking in Chapel. And one of the really nice things was I took this back to the Boeing engineer and I said, well, here's how I'd write this in this language we're thinking about working on. And he sort of looked at it and he kept going, And I was like, oh, this is a domain. These are these arrays. These are different things. And basically he kept saying, well, you've got a bug here. You really should be doing an additional outer to inner at the top level of the hierarchy, or this should really be looking at these siblings. And he was actually debugging my code as opposed to trying to learn the language. And that, to me, was a really good sign that sort of we'd come up with something that was at least more descriptive than sort of Fortran and C, which I guess isn't that hard of a target, but it was nice feedback to get. So let me skip ahead now to just some concluding stuff. There are a lot of challenges in what we're doing here. A big one is user acceptance. This is obviously true of any new language, and the HPC audience is especially skeptical about new languages having been burnt by high-performance Fortran. However, I think that the languages we currently have are inadequate. Therefore, I don't think we can let this stop us. We want to be able to implement this on sort of commodity architectures, not just on the Cascade architecture, but also on clusters and things like that. And I think this represents a lot of challenges. We've designed the language very much with sort of our idealized Cascade architecture in mind. Clusters are not ideal in many respects. They don't have sort of shared global address space, cheap single-sided communication normally. But those are kind of things you'd want for this language. So we have a lot of implementation and performance challenges there, I think. Even the Cascade challenge implementation has a lot of challenges. These user-defined data distributions, I think, are going to be really hard to get efficient. A lot of these language features we've chosen, sort of the type determination of latently with variables whose types haven't been declared, combined with object-oriented programming, combined with overloading, just sort of don't always play together in a really nice way. Parallel garbage collection I mentioned before is something I worry about, and many, many others. So what's next? As I said, phase 2 of this HPCS program ends this coming summer. So what's next is phase 3. Proposals will be going in this spring, and it's expected that 1 or 2 vendors will be funded to go on to phase 3. And phase 3 lasts from something like July 2006 to December 2010. An interesting recent occurrence, though, is that this language effort, Chapel, X10 from IBM, and Fortress from Sun, has actually been sort of forked off from the main part of the program here. DARPA has basically said, well, this language stuff is really interesting, and it's too soon to sort of kick anybody out of those explorations. And so they've essentially said that all 3 phase 2 vendors can go on into phase 3 and continue this language work, at least for a year and a half or so. So they set up this team, the High Productivity Language Systems team, which has a bunch of language people from labs and academia to study and evaluate these languages and report back to DARPA with their decisions and their findings. This will happen in sort of from now to the December 2007 timeframe. And what DARPA hopes will come out of this is a language consortium effort where it's not just sort of the Cray language or the IBM language, but a language that the community as a whole can get behind. And not only the HPC or traditional HPC community, but also trying to involve more mainstream vendors. So there's sort of this question on everyone's mind of, well, multi-core is coming, and how are we going to program that? And is there overlap between these goals? So DARPA is sort of, at this point, cautiously optimistic that after December 2007, there may be this consortium effort that not only involves the Crays of the world, but also sort of the Microsofts and Intels and AMDs and things like that. And that's one of the reasons I'm here today, from my perspective anyway. You might have other reasons. DARPA also hopes to avoid repeating the mistakes of the past. So Ada and HPF are sort of examples of government-dictated languages which never really caught on. They obviously would like this to succeed. So I've been talking to you here today, but this represents the work of many people, both at Cray and our academic partners at Caltech JPL, so I just wanted to call them out. And to summarize, we're designing Chapel to enhance programmer productivity and to address a wide range of workflows. As I described to you today, we have sort of these 4 themes in the language that motivate a lot of the features in the language. The status is we have this rough draft language specification available at a website that's being hosted by the University of Washington. You're welcome to download it and read through it. It's better in some places than others, I'll admit. We're still working on revising it. We're also working on an open source implementation, which is coming along. And we're interested in feedback from users and language people and people like yourself. So that's all I have. I can take any other questions if there are any.
We have time for about 5 minutes worth of questions, and then I'd like to wrap up. We also have some additional time on Brad's schedule this afternoon, so if people want to meet with him, we have 2 one-hour slots that you can come talk to me about, and we'll try to fill that time in. Otherwise, my group will take all of Brad's time. So let's start with Kang Soo.
So in the MTA, you guys had a programming model where you explicitly tried to avoid caring about locality.
Right.
Whereas here you've reintroduced it. Is that because of some epiphany around the Terra model of programming, or was it hardware-driven, software-driven? Kind of what made this change in
That's a good question. And I haven't been at Cray long enough that I can give a very detailed answer to that. But I can tell you that the Cray architectural line has been evolving away from this sort of locality-oblivious model to architectures where locality sort of matters more and more. And this is true both on the vector and on the multi-threading sides of the company. So I actually haven't been involved in the hardware architecture discussions which led to those sort of decisions. So I can't really speak to why that's sort of the way it's evolving. But I think there's a realization that when you have locality, it's nice to take advantage of it. It can be advantageous. And so to the extent that architectures tend to be built that way, it makes sense to take advantage of it. And from our point of view, if the architecture is built that way, the programming model should also be able to take advantage.
Can you give a brief summary of what the status is of the implementation?
Yeah.
Where are you really at with all this?
The implementation is behind where I would like it to be. That's the status. Our first goal was to basically create just a sequential implementation of this that would run on your desktop, so you could play around with things like these domains and arrays and sort of the more novel concepts of language without having a parallel machine or running multiple processes. Also, just to give ourselves an easier target to shoot for. And we still don't have sort of a complete sequential reference implementation yet. What's really happened, I believe, is that, as I mentioned a slide or two ago, the interaction between some of these features like the function overloading and the type inference and object orientation, things like that, really ended up bogging down our implementation efforts much more than we had anticipated. And this may have been just due to the different philosophies of the people who are involved, or just sort of the inexperience for some of us, like myself, in doing sort of this type inference style work. So we're kind of behind where we wanted to be. But it's actually, we've got this sort of critical mass going now where things seem to be added more and more quickly.
So in terms of, now I'll ask the question. So what can you actually run?
What can you run now?
That's what you just described are front-end issues from my perspective as compiler. That stuff's nice, but what I really care about is what can you run?
Right. So our compiler architecture is taking a source code methodology. So most of the issues that you probably care about are going to be front-end issues in the way that we're approaching it. And what can you actually run? You can run some simple array and domain codes of sort of 2 dimensions. A lot of the more fancy kinds of domains that we talked about here are not in there yet. There's a fair amount of type inference built into it. I don't know really how to characterize what you can and cannot run. The main thing we're driving on is trying to get these domains and arrays of sort of these more exotic flavors sort of up and running, but to do it in a way that uses the language features like the type inference and overloading and objects and things like that. And so therefore, that's why a lot of our effort is going into sort of this more foundational infrastructure type of work. So from there, we would go to a parallel implementation. It looks like our short-term implementation will target sort of clusters. And so there are questions there about what to use for sort of the multi-threading layer, what to use for the single-sided communication layer. Currently, we have somebody looking into sort of GasNet and ARMCI, which are 2 single-sided communication layers for sort of commodity cluster systems. See whether either of those will be rich enough to build on top of. If not, we'll use something lower level or maybe MPI, although we're trying to avoid that.
So you won't know how good or bad your cluster version will be until, what, several years from now?
Possibly, yeah. So that's a good question. So these are some slides that didn't fit into my talk. The reason that we're optimistic, though, is due to things like ZPL, which this builds on, as well as HPF, which this builds on. So these are some results from my dissertation and Steve Dietz's dissertation, who's also another team in ZPL. Sort of, these are some code size comparisons between, in each case, an MPI code on the left and a ZPL code on the right. And the main thing to see here is that the ZPL codes tend to be similar or significantly smaller in size, with MG being a nice standout.
Source code, I assume.
This is source code, yeah. And so the idea here is that you can write sort of a compact language that performs well. And these are some speed up charts. So higher is better. The x-axis is number of processors. The y-axis is speed up. The MPI is in blue, and the ZPL is in green or yellow, depending on the version. And again, the point here is to show that we can be really competitive with MPI, which is sort of state-of-the-art in terms of performance right now. And we're optimistic that we'll be able to take these results and carry on this work sort of in the context of Chapel. Rice had some results for HPF, which were kind of similar to this in PPOP last year. And so HPF's another influencer of Chapel. And so again, we sort of hope to build on what they've done. Now, at the same time, Chapel is neither ZPL or HPF. We have a lot of other features. And so there's this question of, well, can you add these other features without losing these performance advantages? That remains to be seen. And unfortunately, yeah, it probably won't be for another year or 2. Any other questions?
Okay, with that, I'd like to thank Brad for his talk, and it was very interesting. And if people would like to meet with Brad later on today, just please come up after in a few minutes after we finish this. Okay, thanks.